Welcome to the technical webinar, 22FDX 22nm FD-SOI Cellular IoT Solutions for Cat M1 and NB-IoT, part of the GlobalFoundries technical webinar series. My name is Sean O'Kane from ChipEstimate.com. We are pleased to introduce the speaker, Anubhav Gupta, GlobalFoundries Director of Strategic Business Development for IoT and Wearables. Now let's join Anubhav to learn about 22FDX Cellular IoT Solutions from GlobalFoundries.
Hello, this is Anubhav Gupta. I am Director for Strategic Business Development for IoT at GlobalFoundries. Today I would be giving you a quick insight in 22FDX and what is unique about this process for the cellular IoT, especially Cat M1 and NB-IoT. So before going into the details of my technical presentation, I would like to give you a quick idea on the IoT market. Right, we have seen 17 billion numbers in 2017, going to 34 billion, and then it's expected to go to 63 billion in terms of semiconductor value for the IoT. So this is a huge growing market, and there are different components on there, which is processing, sensing, and communication. So the place where I'm talking about for 22FDX is basically covers all the three in a single chip. So IoT is a segment where you like to integrate communication, which is RF connectivity, sensing, and processing. And what makes 22FDX unique is what I'm going to talk in the next slides. As a broad portfolio for GlobalFoundries for the IoT, there is a lot of different nodes, but we characterize all the different devices in three categories. One is low, mid, and high, and that is based on computing power, pretty much, and the memory requirement and the things of devices, which is smaller devices, very low power, mid-end devices, which have middle power and computing requirement. But still, all of these have a common theme, which is connectivity, computing, and all of these require low power. Now, from that perspective, if we look at it, from the GF products perspective, 22FDX is a great process node for anything which is low or mid. For the high end, we will say still FD-SOI, like 12FD-SOI, which is a next node from 22. And the 14 FinFET, the FinFET nodes basically would be more relevant for really high-end processing. But 22FDX and the 12FDX are still great for overall for the IoT market. These are some of the products that our customer have already released, and their end customers are prototyping with. One is in the automotive, in the vision processing SoC. Another one is for the industrial IoT SoC applications. Both of them are best in class in terms of both power and performance, and that is made possible because of 22FD-SOI. I would definitely encourage you to go and look for those products, but what I would talk next is basically the next set of products which we're talking in terms of the IoT, which is cellular IoT. So on the cellular IoT, what makes it so interesting? We have not heard of NB-IoT or Cat M in terms of we have heard about it, but we haven't really seen any products. And that's because in 2017, if you look at the TAM numbers, it's pretty low. But in 2021, we expect that TAM to go all the way to 400 million units shipments per year. And that hockey stick growth is possible because these products, or this Cat M1 or NB-IoT connectivity, this is basically giving additional revenue to the carriers without any infrastructure change, pretty much. So it's more of it can basically drive the revenue for the carriers, but with no change in infrastructure. That's a huge thing. To make it will basically drive the subscription price lower, and the higher adoption going forward, because it's pretty much no additional cost to the carriers, and that's what is the reason why you see a big TAM numbers. And another thing which you see very interesting is, although what we expected is 400 million units, but what we see from Gartner is something. Just in China, they are expecting like 600 million connections by 2020. So if you look at that number and if you say that's a reality, then this 400 million may not be 400 million, but it may be 3x of that number by 2021. So it's a huge market that we're talking here. On the roadmap side for GlobalFoundries, the node which makes very interesting for this segment, which is cellular IoT we'll be talking about, is 22FDX and 12FDX. So 22FDX is in production now, and 12FDX is the next node which will go in production in 2019. And both of these nodes are targeted for wireless and battery-powered computing applications. That includes the low to mid application process, IoT, autonomous vehicles, basically, mobile camera, and one of the key things of both these processes is a unique device or a FET architecture that they have, and another capability which is a back bias. And I'll be talking of both of those in the next slides. But both of those capabilities make it so much interesting to do any sort of RF analog in this process. On top of that, it will reduce the overall power consumption of your SoC due to the backgate capability, and I'll talk about those in the next few slides. So just to give you an idea, both these 22FDX as well as 12FDX, so basically FDX Roadmap as a whole is actually architected for IoT, mobile, and RF applications. It enables the differentiated solutions, and when I say that, it is still a planar process, but it enables a FinFET-like performance at pretty much like 28 nanometer cost. So which is a huge thing, and that FinFET-like performance is not just a marketing term; it's basically actual, because what happens is the channel width or channel depletion channel thickness is 6 to 7 nanometer, which is almost 4x lower than the minimum channel length. So what that makes it is, because of that thin depletion region, the characteristic of a device is such that there is no short channel effects pretty much. And that makes it very interesting, because if you talk of any of the lower process node, one of the big issue with the analog is that it doesn't scale with it. But because of pretty much no short channel effects, even in the minimum length devices in FD-SOI, that makes it very interesting for any sort of analog designer, because now you can scale the whole chip by more than Moore's law, basically. As far as the energy efficiency goes, you can actually drive the IoT SoC all the way to 0.4 volts, and that's for the supply voltage. You have a very low leakage, 1 picoamp per micron. You have a very low leakage SRAM as well, which is sub 1 picoamp per bit cell. So all these characteristics makes it very interesting for any sort of battery powered application, and especially IoT. And so if I look at overall, what are the key things in there? You have a near FinFET-like performance. You have an additional back gate, which is basically due to the thin buried oxide insulator in there. You have another control of threshold voltage. And you have basically fewer masks overall versus even 28 nanometer. And that makes it very cost competitive to 28. So effectively, there is no, if you are designing anything, if you're looking to design anything right now, rather than doing anything in 28, you would rather do it in 22, because you are getting both the cost advantage and the performance advantage with 22. So 22 is, you can consider as more a superset of 28. You can do not just the digital design in there, you can do analog design as well, and it scales and it's lower power. So overall, you will get a much better performing product with 22FDX. As I mentioned, this is already in production. We have gone through it's already production qualified in March, and right now the products are taping out for production with multiple customers. So when I talk of this FD-SOI versus bulk, right, so I do want to highlight that particular aspect of the unique device structure. What you see in there is this box, a buried oxide substrate, in there, and this is a very thin oxide. What it does is it gives you a second back gate which you can actually control. So think of it, you have a front gate which is in the path of a signal, but you have a back gate through which you can actually control the threshold voltage even after the production. So which gives a huge benefit in terms of either controlling your power when you want to run your SoC faster, you actually reduce the threshold voltage. When you want to reduce your leakage, you actually go back to no threshold, power in the back gate. So overall, it will give you a huge flexibility in terms of controlling the leakage or the performance in the digital SoC. We'll talk about next on the what it gives to the analog, right? So because of the thin depletion region versus so the reason why you have the short channel effects in general is because your depletion channel thickness is close to your gate length. Now in this case, depletion channel thickness is fixed by almost 6 nanometer or so because of how its device is constructed. So once your depletion channel thickness is fixed to 6 nanometer and your device lengths are 24 nanometer, what happens is the effect of short channel is almost negligible. And that is a unique thing which makes it possible for analog design to do even with the minimum channel lengths. There is the source and drain to well capacitor with almost nothing basically, and it is not dependent on the bias. So normally when you change your voltage versus the substrate, you have a change in the capacitor of your drain and source, which is not the case here because the substrate is isolated by your box or buried oxides. And then you don't have pretty much any source or drain junction diode, which is another very big advantage in doing the analog design. And another thing is there is no concern of latch up because of your voltage of your substrate going higher than your drain and source, and so it's basically because you have a direct oxide in there which limits any sort of currents flowing even if you have your well going at a much higher voltage, which actually we use as a backgate voltage, and that helps in the design. So it is a unique device structure which you are getting at pretty much the cost of the 28 nanometer, and that makes, with that flexibility, it's both a big advantage for the digital designers as well as a big advantage for analog designs, and that's what makes it very interesting to do the products for cellular IoT. Okay. In July, we announced that we are, or GF is going to work with VeriSilicon to do a single chip solution for narrowband IoT and LTE-M or Cat-M application. And this is, when we talk of single chip, that single chip is not just the modem or the RF. It basically includes the RF front end, switches, filters, and everything, even including the power as a single chip. That's what single chip means. And that the concept of cellular modems is that you have multiple dies in there, and then you put together a one modem, more of like a multiple die in a package. That is not the case here. What we are talking is actually a single die solution, which is revolutionary. And that will really disrupt this market that we believe is only possible because of 22FDX properties. From the perspective of, if I look at the hardware difference, we'll be doing both the NB-IoT only and LTE Cat-M. The primary difference comes in the baseband. The baseband is more complex for LTE-M versus the NB-IoT, and also the memory requirement is almost double or more than that for Cat-M. So the SRAM is bigger. So that creates the difference in terms of hardware. But why are we doing this basically? What we see is this is more driven by the market factors. So Cat-M1 is necessary for US market because you already have a LTE network in place, and Cat-M1 gives you all the advantage in terms of speed as well as not a big penalty in terms of power. But NB-IoT has a much bigger flexibility in terms of network. It can run on GSM as well as LTE network, and that makes it very interesting for both the Europe and the Asia market. And that's why you see a big push from the carriers in both those regions. But there is also an advantage for Cat-M1 in terms of voice and mobility, basically. So it supports cell handoff versus the NB-IoT doesn't support that. And that makes it interesting even for the Asia and Europe market. So when you see this Cat-M1 advantage for both voice and mobility, and when I say mobility, that means cellular handoff, that both these advantage makes it very relevant for even the Asia and Europe. So you will see both of these standards there, but for the application which will require NB-IoT only, what we are trying to do is eliminate any penalty in terms of the cost and have it only for Cat-M1. So if you go to looking at what really makes it interesting for the cellular IoT application, right? The 22FDX. One is it has a very high linearity switches with a very or high background voltage. That makes it very interesting for any sort of RF front-end switches. Second thing is it can support 23 dBm or peak power of even 30 dBm PA. That can be integrated because it can support active FET stacking. Just to give you an idea of what that means basically, when we talk of FET stacking, that is possible because there is no drain to bulk capacitor there, drain to bulk or source to bulk capacitor there. So you can actually stack the devices without much loss of power because of those caps. And that is very interesting for 22FDX because of that buried oxide in there, that oxide which isolates and make it SOI. That oxide removes that drain to bulk or source to bulk capacitor, which is typically present in CMOS bulk processes. So that makes it possible to do FET stacking, and even though it has a high breakdown voltage, it can basically do much higher PAs basically in 22FDX, and that is critical to achieve that. Another thing is because of the channel properties, and you can do the products with a much shorter channel length versus what analog products and with much shorter channel length than what you can do in the bulk process. What it enables is it has a very high self gain because you don't have much of channel length modulation there, and then on top of that, with that self gain, because of with the smaller FET and the smaller, you can have much higher GM, you can have a much higher FT. So your unity gain frequency is much higher, or you can achieve much higher unity gain frequency with the FETs that can be usable to do the amplifiers, right? And so that makes it interesting to reduce and enable the inductorless LNA. Another thing is due to the switch characteristic and with the use of the backgate bias, you can achieve very high linearity for any sort of data converters and actually reduce the size of your devices by almost 5x for your data converters, the switches, and that is a big advantage both in terms of size but also in terms of the power consumption or dynamic power consumption in your data converters, switch cap circuits. Another thing is availability of LDMOS. What that does is basically it removes the requirement for external PMU and you can actually integrate the PMU, including the switcher for the PA on the chip. And that is a huge advantage in terms of getting the whole solution in a single die. It's a much simplified design. You can actually use the backgate bias to bias your design instead of putting everything in your signal path, and that simplifies your design overall with least of the losses. It has a 4x better mismatch. Just the device itself has a 4x better mismatch than the equivalent design or device in 28 nanometer bulk. It has a 5x better noise performance than your 28 nanometer bulk. And what does that mean basically? You can actually, to get the same performance in terms of mismatch, in the same performance in terms of noise, you can have almost 4 to 5x lower area of your FETs. And that's a huge advantage. You are basically going even more a reduction than any of the Moore's law can do for a digital. On the digital side of thing, if you look at it, with this unique body biasing capability, which we're talking of backgate bias, you can actually operate at 0.4 volts supply. Another thing is it has a very low leakage in terms of almost less than a 1 picoamp per micron. It has a SRAM retention current of less than a picoamp with a SRAM retention voltage in 0.5 or in that range, 0.5 volts or so. And it has a very fast wake up via on-chip EMRAM. What is EMRAM? EMRAM is basically an alternative non-volatile memory versus the flash that we enable on 22FDX. It has pretty much the similar read speed as what you talk of flash, but the key thing which is very different is almost 1000x better speed of write. So basically this memory can be used in conjunction with your SRAM together on the chip instead of having external flash, and it will reduce the overall area of your EMRAM or flash plus SRAM combination that you may have in the previous chips. And last thing on this one is you can actually control the independent blocks not just by turning off the power supply, but you can actually reduce the leakage when you're standby by controlling the backgate. So you can, when the case is when you have to run your processor faster, instead of designing with really for run faster, you basically use your back bias. You do the forward back bias, you have the application timing done with that one, run it faster. But when you are in standby, instead of turning off really the supply, you basically use your backgate to reduce your leakage. So you remove the backgate bias instead of forward biasing it with 2 volts or so. You basically remove it, get it back to 0, and that reduces significantly your leakage because VT is reduced without removing the power. So that will help come up very quickly because backgate is still not a big current consumption. It's just a bias basically. So that would help you wake up very fast from the standby going to the active mode. So I will talk of couple of few key things that would make it very interesting from the perspective of 22FDX, and one of the things is adaptive body bias. What does that do? So normally if you look in, you will have a big spread of your process. Yeah? You have a slow corner, you have a fast corner, and when you design for a certain operating frequency, you basically design pretty much or close your timing for with the slow corner. And because of that, your design becomes bigger, you have higher leakage, it's not most efficient. To achieve efficiency, you may probably do the dynamic voltage scaling, and in that case, you will lose power basically when you have a chip which is slow corner. So what this back bias is doing is, rather than doing or increasing the voltage by doing dynamic scaling and all those things and increasing the area to compensate for the slow, what it's doing is it says we enable the library where you can actually design with a fixed voltage, which is the lowest voltage for the fast pass, or and then you basically use the back, you do the process monitoring, which you are anyway doing right now. You do the process monitoring and temperature monitoring, and you move your slow corner with the back bias. So you basically do the forward back biasing to basically make the VTs lower and move the slow corner more closer to their fast. So what that does is basically it makes your spread of your variation much smaller. So for doing the timing, you have your circuit would be much smaller, your leakage would be lower, and you would be running at a fixed supply instead of varying the supply and increasing the power when you are going for a higher supply. So that is a big advantage that you can get by using the backgate instead of using the supply. And it will both improve your power consumption, it will be a better area optimization basically, and that is something which is a unique benefit for the digital that we are enabling with the library. And this is something for the IoT specifically. We are enabling a library which can do 0.4 volts supply for application which is sub 200 megahertz and more of in the IoT realm basically. But this same concept can be applied for even the higher frequency. So there is no limitation there. And we will definitely work with customers on that depending on the requirement. So normally chips age over time, and you can basically compensate for that aging with the back bias. So think of it as another lever that a designer has to do a better design and have it much long laster with the best performance possible even after several years. Another thing is you can actually, so this is basically just the compensating for the process variation and temperature variation, but you can actually overall boost the design by even in the fast pass corner. If you want to give a boost, you actually move the whole distribution to the higher frequency, almost by 30% higher frequency that we see by adding the back gate, even in the case of your fast corner. So this is basically this overall gives you it's a big flexibility for the digital designers basically when they are doing the digital SoCs of improving the performance while not really going for the next node. So it gives you both the boost in performance and lower power because your supplies are lower now. So this is as I talked before, one of the things is you can achieve the FET stacking, and that is possible in FD-SOI instead of the bulk because of no drain to bulk or source to bulk caps, and you can stack the devices with no capacity, and you can achieve much higher voltages that is required at your output without losses in the capacitors in the drain and source. So this is a very interesting thing that is possible with the FET stacking that you can do in FD-SOI. Another thing is the breakdown voltage is much higher in general because of the FET characteristic, and that makes it also very interesting for doing the integrated PAs on the chip with the rest of your RF. This is, as I talked before, for the data converters, 22FDX is pretty much the best switches you can get for the data converters. And the reason for it is because normally in data converters, your noise is driven by the KT over C thermal noise floor that you have there. So capacitor drives the noise. But what you do is, based on your input frequency and your Nyquist frequency requirement, you switch at a certain frequency your gate or the FET. You switch your FET at a certain frequency that is driven by your input signal. When you switch at that frequency, you need a certain RC time constant. So the output signal on your capacitor settles to a certain value. To achieve that, you design your FET, or you make sure that the RDS on is a certain value for your switches. Now that RDS on is driven by what is the maximum value of the RDS on for that switch over the whole input signal range. So that means is, if you look in here in the curve, there's a yellow curve which is basically 28 SLP bulk. I took a PN FET. You have a lower resistance when your PFET is on, and then when you have InFET is on, you have a lower resistance on the two sides. But in the middle, where both of the FETs are on, you have a higher resistance. That is the one that you use for your IC time constant. So if you look from that particular aspect, it is fairly high. Now, if you apply the back bias, what you see is with the back bias of say 0.8 volts, you have this green curve, which is fairly lower. But with the like almost like a 2 volts of a back bias, you make that change of RDS on of that FET or the switch pretty much very linear over the whole input range. That is very interesting because you are basically getting you can do the same requirement that you have for data converters. You can do it with a 5x lower switch area, and that 5x lower switch area converts to 5x lower power, dynamic power. That 5x lower power converts to the 5x lower drive circuit or load circuit that you have, which is driving that switch. So overall, it's a cascade effect to make it both lower power, lower area. If you and beyond this, the lower power and lower area, because your switch characteristic or switch RDS on is basically flat over the whole input range, you make the output much more linear than what you had before, and that is very interesting. So with the back bias, this is a huge advantage for any sort of high-speed data converters or switch cap or any RF front-end switches to use the back gate and take the advantage of the linearity that it creates and the lower RDS in the smaller area. So we have a myth that analog doesn't scale, and that myth is more driven by CMOS bulk technology, because as we go lower in the process geometries, our length reduces, but what happens is length became more and more, channel length became more and more closer to the depletion width of the depletion channel, and that width, when I say width, I would say rather depth in the depletion channel, and that depth, when it becomes closer to your gate lengths, okay, you have a big disadvantage, the short channel effects. So you have channel length modulation, you have velocity saturation, you have dibble. All those issues comes in picture when you have when your depletion region depth is closer to your or similar to your channel length. Now that thing, so that makes it not possible to do the minimum channel lengths. The channel lengths are 4-5x bigger than the minimum channel, or even more actually, to do any sort of analog design. And that's a huge disadvantage, and that's one of the reason why you cannot scale analog in CMOS bulk technology. So even if you are going from 40 nanometer to 28 nanometer, you don't scale the lengths. You basically make the same lengths as whatever is in the 40 nanometer. In terms of the mismatch, it's inversely proportional to the device area. So you cannot much reduce the mismatch. Means you have the even if you're going from 40 to 28 or say 90 nanometer to 40 nanometer, whatever the case is in the bulk, you cannot reduce the mismatch. So you basically have to keep the same device area to achieve the same mismatch. As far as flicker noise goes, same thing goes there. It's proportional device area, inversely proportional device area. It's once your device area is a certain value, you basically have a certain flicker noise. So you make the devices bigger, even when you are going for a shorter geometry where your digital is scaling. You cannot scale the analog because you have to make the devices bigger to make sure that your flicker noise in the same has the same performance as the previous node. So what's the solution when moving to a lower geometry process? The solution is that, yeah, you make the devices the same. You take the analog block that you had in the older geometry process. When you move to a new geometry, you scale the digital, but you don't scale the analog. You take the same circuit and you put it back in the shorter channel, shorter geometry, basically. No analog scaling. What does that mean? Yes, that's what you have to do to achieve the same performance. But does it make sense? And the thing is, that has been the case till now. But with the fully depleted thin channel, or 6 nanometer sort of thickness of or depth of the channel or the depletion region, FD-SOI is not the same way. In the FD-SOI, analog does scales, and we'll talk about that in the next slide. And in the analog, in the 22FDX, analog design scales even more than Moore's law. Short channel effects negligible in 22FDX, and the reason, as I mentioned before, is depth of the depletion region is fixed by the construction of the device. So because of that, your channel lengths are almost 4 to 5x of your depletion region width or depth, basically, and that makes it very interesting. So pretty much short channel effects are negligible in there. Mismatch, because of the way device is fabricated in the 22FDX, we have noticed directly almost half the mismatch in the 22FDX versus 28 nanometer bulk. We have 4x lower mismatch in 22FDX, and the reason for that is the fabrication of the 22FDX devices versus the 28 nanometer bulk. That just fabrication itself gives us almost half the mismatch, both in PMOS and NMOS, and that almost half the mismatch converts to 4x in terms of area, because mismatch is inverse proportional to square root of the area of the device. Flicker noise, it's just exactly same way, just the device property itself. When we compare the 22FDX flicker noise property to 28 nanometer bulk, we have seen almost 5x better flicker noise. Again, flicker noise is inversely proportional to area. So you have a bigger area, you will have lower flicker noise typically, and that's why you see a lot of big FETs there when you have to do low circuit which is affected by flicker noise. That is not really required in 22FDX. You still have the area, you will still do the bigger area for flicker noise, but you can actually scale by almost 5x for the same performance in 28 nanometer bulk in 22. So you can scale the area by almost 5x in 22FDX. So analog overall, because of pretty much no short channel effects, 4x lower mismatch, 5x lower flicker noise, you can actually scale analog by almost 1/4 or up to 1/4 in 22FDX. Now you can obviously decide on improving the performance, and you may not go to exactly 4x improvement, but if you really want to achieve the same performance, there's a potential to scale the analog by almost 4x in 22FDX. So as analog scales in 22FDX versus bulk, what that means, you have smaller gate caps for the same transconductance. Because you are shrinking the channel length, you are shrinking the channel width basically, and overall you are getting the same transconductance but at a much smaller gate cap. What that does, basically it enhances your unity gain frequency, FD, and then also the F max because of the higher self gain. And that is a big advantage. Both FD and F max are significantly higher than your bulk CMOS process, and that makes it very interesting for both RF designs or low power RF designs, as well as what we see is because of FD and F max in the 300 gigahertz range, you can actually do more of a millimeter wave circuits as well in the automotive and other applications, and that millimeter wave 5G circuits as well, which makes 22FDX makes that possible. But importantly for IoT, This is another thing which is very interesting for doing low power designs. Lastly, I would like to highlight on this EMRAM, right? This is a unique capability that we have added in 22FDX. One of the very important things in the EMRAM is it has basically both the size and the power advantage versus the flash. In terms of the write speed, it's almost 1000x better than the flash. So you can actually use it. Not typically we saw the flash, we only use it external, or you use it for storing the code or so. You can actually do that, but it also can work with your SRAM as a secondary memory and scale your SRAM in the regular operation because it has a very fast write speed. It has much higher endurance. As I talk, it is much more versatile because it can be used as a code storage as well as working memory. Size is pretty small, as you see in there, 0.047 square micron, and the data retention, it meets the solder reflow, which is a very important requirement for the auto grade. And we would be doing we are also qualifying this EMRAM for the auto grade. So what in the summary I want to talk about is 22FDX technology has something unique because of negligible short channel effects even for the minimum length FETs. It has 4x lower mismatch for the same device size if you compare between 28 nanometer bulk and 22FDX. It has 5x lower noise for the same size device between the two. So overall, what it does is you can actually scale analog and RF designs in 22FDX without being concerned of short channel effects. Okay, that's one thing. The second thing is it gives you unprecedented design flexibility because now your threshold voltage is not just controlled by the process. You have an extra control of your threshold voltage via a backgate bias. That makes it possible for you if you have a certain requirement on your operational frequency, and because of process you have some issues after production, you can actually control it by a backgate. So that gives you additional flexibility, additional knob in there which you didn't had before in any of the bulk processing. And that also applies to even the FinFET. Basically you don't have it. Yes, FinFET devices are very similar to 22FD-SOI in terms of, because it's also a thin depletion. That is fine. So, but the thing is, you don't have that flexibility in even the FinFET to have that backgate to control on the fly your speeds of performance or power. Then exceptional linearity of switch. So as I mentioned to you, it has something which is the switches are linear, but on top of that, with the backgate bias, you can make it really flat over the whole dynamic range, as I showed in the previous slides for the data converters and switch cap circuit. Exceptional linearity. Adaptive backgate bias, as we talked about, can achieve lower power without doing the dynamic voltage scaling. If you want, you obviously have still dynamic voltage scaling is available to you. You can obviously do that, but even if you don't want to do that and you want to achieve that for the lowest voltage, you want to compensate for your process and temperature variation, you can do that with a new knob now, which is a backgate, and that is something we are enabling in the library itself. And so you will have the smallest area because you now design for pretty much the fast corner or much higher frequency. You design there, you don't have to take the baggage of the slow corner circuit, and on top of that you will have a lower voltage overall, so you will have a much better power consumption. Fastest and lowest power in non-volatile memory that we enabled as a EMRAM in 22FDX. That's a huge boost because now you don't think of it as something to store your code, but you can actually use it as a working memory as well because of its high, almost 3 orders higher speeds of writes versus the flash. Overall, because of the device properties, especially for the RF, integration of LDMOS for the PMIX, and the lowest power digital SoC that you can do using the back-bias capability of 22FDX, you will get the smallest, lowest power. And then obviously once you are smallest and most integrated, you will have a cost optimum for the IoT application. You are not talking of a lot of BOM around it. You are basically reducing the whole thing to a single die and integrating most of it basically on the chip, and that makes it a cost optimum overall. So that makes it very interesting for the IoT connected or RF IoT with the SoC power, everything in there as one single chip solution for the IoT. And that is what we are doing, not just for Wi-Fi, BLE or the existing standard, but also new standard like cellular IoT, which till now has been dominated by multiple dies in a package. Now we are talking of single die solution for the complete cellular modem. Thank you for attending.
Thank you for joining us for the webinar 22FDX 22nm FD-SOI Cellular IoT Solutions for Cat M1 and NB-IoT. If you have any questions, please email them to marketing@globalfoundries.com or contact your local GlobalFoundries office. Also, for more information about FD-SOI, FinFET, ASIC, RF, and other technologies can be found at globalfoundries.com.